Good morning, students. I'm Dr. Kavitha, Professor, Department of Physics from Dr. MGR Educational Research Institute. Today, I'm going to take a topic, liquid model from nuclear physics for second BSc Physics. Nuclear models. In this first, we must know why is the binding energy per nucleon almost constant? Why do certain nuclei emit alpha and beta particles? Through these particles do not exist inside the nucleus. Why are the nuclei containing 2, 8, 20, 28, 50, 82 nucleons most stable? Like any other quantum mechanical system, a nucleus also exists in its excited states. The most stable state is the ground state in which the nuclei are generally found. There are different models. First one is liquid drop model, shell model, collective model, and optical model. Nuclear models. The first one is the liquid drop model or water drop model. Second one, shell model. These two models, they describe the aspects of the structure of nuclei and how they behave. Liquid drop model. Assumptions. The nuclei of all the elements are considered to behave like a liquid drop of incompressible liquid of very high density. In an equilibrium state, the nuclei of atoms remain spherically symmetric under the action of strong attractive nuclear forces, just like the drop of a liquid which is spherical due to surface tension. The density of the nucleus is independent of its size, just like the density of liquid which is independent of its size. The nucleons of the nucleus move about within a spherical enclosure called the nuclear potential barrier, just like the movement of the molecules of a liquid within a spherical drop of liquid. The binding energy per nucleon of a nucleus is constant, just like the latent heat of vaporization of a liquid. Volume energy. As a first approximation, we can think of each nucleon in a nucleus as interacting with its nearest neighbors. So the energy associated with each nucleon is considered to be U. Because each bond is shared by two nucleons and therefore each has a binding energy of half U. So volume energy, we are after deriving, we got the equation as EV is equal to small a1 into capital A. It is volume energy. We know if the nucleus is spherical, then a volume of a sphere is 4 by 3 pi r cube. So 4 by 3 pi r cube is approximately equal to A, mass number. Surface energy. The surface energy is proportional to surface area. It is also proportional to 4 pi r square. If r is equal to r naught a power 1 by 3, then surface energy is proportional to 4 pi r naught a power 2 by 3. So surface energy is equal to minus a to a power 2 by 3. It is important for lighter nuclei since a greater fraction of these nucleons are on the surface. The next one is Coulomb energy. The repulsion between each pair of protons in the nucleus also contribute towards decreasing its binding energy. The Coulomb energy of a nucleus is the work that must be done to bring the protons from infinity into spherical aggregate. The size of the nucleus V is equal to minus E square by 4 pi epsilon naught R. Since there are Z into Z minus 1 by 2 pair of protons, so Coulomb energy EZ is equal to Z into Z minus 1 V by 2. So finally we derive, we get the Coulomb energy as EZ is equal to minus A3 Z into Z minus 1 by A power 1 by 3. The Coulomb energy is negative because it arises from an effect that opposes the nuclear stability. The binding energy per nucleon. The total binding energy of a nucleus E is equal to EV plus ES plus EC. That is, the total binding energy of the nucleus is equal to sum of volume energy surface energy and Coulomb energy. So volume energy A1 capital A, surface energy is A2 A power 2 by 3, and Coulomb energy is A3 Z into Z minus 1 by A power 1 by 3. Finally, the binding energy per nucleon is E by A is equal to A1 minus A2 by A power 1 by 3 minus A3 Z into Z minus 1 by A power 4 by 3. The drawbacks of liquid drop model. It is not able to explain the magic numbers. It is not able to explain the excited states. It's not able to calculate the nuclear applications of liquid drop model. The main achievements of liquid drop model, it explains the binding energy of large number of nucleus. It explains the fusion and fission process nicely. It explains the energy of radioactive decay, fission and fusion. And also the applications are very large nucleus breakup, nuclear fission and nuclear fusion. Thank you. If you are having any doubt, you ask me.